Hello and welcome to the second week of getting started with competitive programming on NPTEL. I hope you've been having a great time in the course so far. So this week we will be focusing on searching and sorting based problems. Of course, these are really fundamental techniques, and it turns out that they are extremely useful in competitive programming as well. They show up in all kinds of complex problems, either as pre-processing routines or as useful things to do here and there, or as the thing that helps you get to the final answer at the very end. So it's a good idea to develop some degree of competence in using these techniques. And for the most part in this week, we will be focusing on identifying the fact that these techniques come into play. So in particular, we will not really be worrying about implementing classic sorting algorithms like, say, insertion sort or merge sort or quick sort or whatever. If that's something that you feel like doing just to brush up a little bit, then there is a great sequence of exercises on HackerRank, and you can go and try that out. If you just want to brush up on the concepts, then there are some really nice articles on Khan Academy, and I'd recommend those as well. You can find the links either in the description of this video below, or you can find them on the prerequisites page for week 2 on the course homepage. So please go ahead and take a look in case your background in sorting algorithms and binary search is a little bit rusty, because that will be helpful as you come back here. Another thing that is worth doing in preparation is to look up the documentation for the built-in sorting functions in your language of choice. So make sure you know what parameters they take in and whether they have any extra superpowers, and also just double check that you know how to do simple related tasks like, let's say, sorting an array in reverse order or sorting a subarray and things like that. So with all that said, we can now begin our discussion of the first problem for this week, which is Treble Sort. It's once again a Google Code Jam qualification problem from back in 2018. And it might remind you of reverse sort because there are some reversals happening, but of course it's quite a different problem. So let's get started. So let's begin as usual by going over the problem statement. So we are introduced to Treble Sort with some background on bubble sort to begin with. So remember that in bubble sort what happens is that we do repeated passes over the array, and in each pass, whenever we encounter a consecutive pair of integers which are out of their natural order, then we swap them to fix it. So that's what bubble sort does. And now the problem statement authors claim to have come up with a better or an enhanced version of bubble sort, where instead of considering a pair of numbers at a time, they're going to consider triplets of numbers at a time. And if a triplet is out of order, by which they mean that the last number in the triplet is smaller than the first number in the triplet, then they're going to reverse this entire triplet. Okay, as opposed to swapping adjacent numbers, this entire triplet gets reversed. Notice that when you reverse 3 consecutive numbers, the middle number actually stays in place. It doesn't shift in any way. So that's essentially Treble Sort, and they claim that the reason it is named like this is because it is short for a triplet version of bubble sort. So there's always a cheeky remark in the code jam problem statements, and this is the one for this example here. So let's take a look at the pseudocode for Treble Sort just to make sure that we are on the same page about what it does. So there's going to be a flag variable done, which basically keeps track of whether we have managed to sort the whole array or not. So if done is true, then that means that we can stop doing any further passes on the array. So as long as you're not yet done, well, let's hope that we are going to be done this time. This is our lucky day. So we initialize done to true, and then we start our pass. So because we're looking at triplets, we don't have to go all the way up to the n-1th element. We only go up to the n-2th element, because otherwise you'll just fall off the cliff, so to speak. By n, I just mean the length of the array. So I'm using n to denote len of L. And now what happens in the ith iteration is that you compare the elements in L of I and L of I plus 2. So these are the extreme points of the triplet that starts at the ith location. Now if it turns out that these elements are out of order, so the element that appears earlier is larger than the element that appears later, then we reset the done flag to false. We say, okay, we did encounter a problem. This array was not sorted in its present form, and to fix this particular aberration, what we will do is we will reverse the sublist from L of I to L of I plus 2. Essentially, once again, notice that this amounts to swapping the elements at L of I and L of I plus 2, because the middle element, which is at L of I plus 1, stays in place during this so-called reversal. So that's it. That's pretty much the entire algorithm. You keep fixing triplets for as long as you need to, but when you finally are able to make one full pass without having encountered any broken triplets, then you stop. So as usual, to understand what's going on, it's useful to walk through an example. So let's just go over the worked out example that's given in the problem statement. So we have an array here with 5 elements, 5, 6, 6 and 4, 3 in that order, and the numbers written just below these elements are the corresponding array indices, just for our reference. So let's go over a run of Treble Sort on this array. To begin with, the variable done is initialized to false and I is not initialized yet, but we'll get to that in a minute. We of course enter the while loop and reset done to true to begin with, and we initialize I to 0. And notice that in the first iteration of the for loop, we are comparing the elements at L of 0 and L of 2. So those elements happen to be 5 and 6, but notice that the conditional doesn't really trigger because 5 is not greater than 6. So we move on. We go back to the for loop, we increment I to 1, and now we are comparing the elements L of 1 and L of 3. However, this time the conditional will trigger because 6 is in fact greater than 4. So we enter this if block and we reset done to false. This is essentially a note to say that this pass did have a problem, so we just want to flag that for ourselves. And of course in the next step we will try to fix this aberration by essentially swapping these two elements. Of course the language here is that you reverse the sublist, but as we have mentioned earlier, that's the same as swapping the endpoints. So this is now done, and we can go back to the next iteration of the for loop. At this point I gets incremented to 2, and we are comparing the elements at L of 2 and L of 4, and once again notice that 6 is greater than 3, so the conditional will trigger. Done is already false, so we don't have to do anything there, but we do have to execute the swap. So at this point the array looks like 5, 4, 3, 6, 6, and now if we go back to the start of the for loop, I is incremented to 3, but notice that there is no triplet that starts from L of 3, and in particular we've just run out of room. So this this iteration is done, and we now go back to the while loop. And are we done? Well, the value of done is false. Remember we had a warning that this pass had some issues, not all the triplets were properly placed, so we need to do another round of checking. In fact, if you look at the array right now, it is not yet quite sorted, so it's a good sign that we are giving this another shot. So once again we'll begin by resetting the done variable to true, and then initialize the for loop. So I gets reset once again to 0, and this time notice that when we compare the elements at L of 0 and L of 2, this is no longer a valid triplet. So since 5 is in fact greater than 3, we do need to execute a swap, before which we should also remember to reset the done variable as before. So done is now false, and we have the swap between 5 and 3. So we go back to the start of the for loop, and and we increment I to 1, and at this point we are comparing the elements L of 1 and L of 3. Now notice that this pair of elements is already in the right order, so we don't have to do anything. The conditional does not trigger, and we go back to incrementing I to 2. Now when I is equal to 2, we are comparing the elements 5 and 6. Once again, these guys are doing fine, so we don't need to do anything here, and we go back to the for loop. But once I is incremented to 3, we have essentially run out, so we go back to the start of the while loop now. And once again, notice that we are not done yet, so we'll have to do this one more time. And once again, we reset done to true. But this time around, notice that every time we compare these triplets, everything is going to work out. You can see this by just observing that the whole array is sorted. So in particular, you will never encounter a triplet which has its elements being in the wrong order. So everything works out here, and we are in fact this time done, and the algorithm stops with the array state being 3, 4, 5, 6, 6, which of course looks pretty good. Everything is sorted, and you might be tempted to think that Treble Sort is a real sorting algorithm after going through this example, but it turns out that that would be quite misleading. So why don't you take a moment here to try Treble Sort yourself on this small example. Please take a pause, actually think about what Treble Sort would do, and also see if you can come up with your own examples where Treble Sort has suspicious behavior. Alright, so hopefully you had a chance to take a look at this, and if you did, you would have realized that Treble Sort is not going to successfully sort this array. In fact, the only elements that it has a chance to compare are the elements that are at indices 0 and 2, and those of course seem to be perfectly in order, but you can see that the overall array is certainly not sorted. So Treble Sort does fail at this point, and in fact that turns out to be the problem statement. So it is our task to figure out if a given array gets sorted by Treble Sort or not, and further, if Treble Sort fails, we also have to identify the first point of failure, which is defined as the smallest index with the property that the value at that index is larger than the value that immediately follows it in the array after Treble Sort has finished processing the array. So of course you might be thinking that Treble Sort looks like a reasonably straightforward algorithm, so why not just simulate Treble Sort on the input array and check if the resulting array is sorted or not. And that's a perfectly valid approach, but to figure out if that's going to be feasible, we'll have to think about the complexity of running Treble Sort on a given array, and then we have to take a look at the problem limits. So let's address the first question first. Once again, take a pause here, go back in the video if you need to look at what Treble Sort is doing more closely, and think about what would be a valid upper bound for the complexity of Treble Sort when it is run on an array with n elements. Come back when you're ready. Okay, so hopefully you had a chance to think about this. Let's just take a look at the pseudocode for Treble Sort again. You'll see that there is this for loop that clearly runs for n iterations, n again being the length of the array that we are working with. And the real question is, how many times do you run this for loop? Well, that's going to be as many times as you need to run the outer while loop. And you can probably come up with examples of arrays where the outer while loop actually runs for n many iterations. So since that can happen, we know that there are certainly instances where the running time can be as bad as n squared. It turns out that the running time can in fact also be bounded by n squared. It's never worse. You can show that the outer while loop will never execute more than n times, and the reason for this will become clearer as we go along. If I try to explain it fully now, then I'll also have to say spoiler alert and all that, so I will postpone this for now, but hopefully you had some intuition for why the answer to this question was order n squared. So the question is this going to be a reasonable strategy for us? For this, we need to look at the limits of the problem. So it turns out that our arrays can have as many as 10 to the 9 elements. So order n squared algorithm is not really going to work out. So we need a slightly different approach. So let's go back to the drawing board and really look a little bit more deeply into what Treble Sort is doing. So here we have an array with 6 elements, and I have pulled out the most crucial part of the Treble Sort pseudocode, which emphasizes what's happening during the passes. So let's take a look at what happens when we do one pass over this array. In the first iteration, the first and the third elements get compared. In the second iteration, the second and the fourth elements get compared. In the third iteration, the third and the fifth elements get compared. And in the fourth iteration, which is the final iteration, the fourth and the sixth elements get compared. So notice that the green elements get compared with the green elements, and the pink elements get compared with the pink elements in every single iteration. And in particular, a green element never gets compared with a pink element just by design. So in some sense, because you're skipping over the middle element of the triplet whenever you're considering a triplet, you never have a chance to compare an element which is sitting at an odd index with an element that is sitting at an even index, which means, of course, that there are going to be a lot of lost opportunities. So if you remember the array 1, 3, 2, this is exactly what was happening. But now if you think about what Treble Sort actually manages to do, it can be thought of as two independent runs of an algorithm that you are already familiar with. So again, take a moment to pause here and think about if you can fill in the blank in this sentence. And the sentence is the following. So Treble Sort is just two parallel runs of which algorithm? And by parallel, don't take that word too seriously. What I mean is that it's essentially running a familiar algorithm on some subarray, and it's running the same algorithm on another subarray. Can you think of Treble Sort this way? Okay, if you've had a chance to think about this, you might have come to the conclusion that Treble Sort is essentially just bubble sort being run separately on the subarray that consists of the odd indices and separately on the subarray that consists of the even indices. So what's really happening is that you can think of Treble Sort as sorting the even indices separately from the odd ones and then putting them back together. So this is a really useful perspective on Treble Sort because it allows us to implement Treble Sort without really implementing it. So in particular, what I mean is what we want to do is take an array and figure out what is the array that Treble Sort would output if it was working with this given array as input. Now we want to get to this information without actually literally implementing Treble Sort, but now knowing what Treble Sort is effectively doing, we can do this, in our own way. So I think by now you have enough hints to piece together the final algorithm. So if you want to take a pause here, this would be a good time to try and figure out the rest of the details yourself, and then come back to exchange notes once you've given it a shot. Alright, so here is what you could do with the information that you have at hand. So to begin with, you could split the given array into odd and even subarrays. By this I mean just collect all the numbers that are sitting at odd indices and declare that to be your first array, and then separately collect all the numbers that are sitting at even indices, and this becomes your second subarray. Now you could sort these two subarrays independently, and here crucially remember to use a efficient sorting algorithm. Don't use something like bubble sort to stay true to the spirit of Treble Sort or something like that. That would just bring you back to square one in terms of an inefficient implementation that will definitely time out. So at this point, use a built-in sorting function, or even if you're using a sorting function that you have written, make sure that it's based on an order n log n kind of algorithm, right? So sort these two subarrays independently and then just splice them back together. So just put them back to one big array with the odd elements being in the odd positions and the even elements being in the even positions. And now if this array is sorted, then you can say, okay, I think that is what you have to output if treble sort actually works. Otherwise, you can just do basically one pass over the array to figure out the first inversion that you encounter. So what you want is the first pair of adjacent elements that are out of their natural order, and that's fairly straightforward to do. So at this point, I think we have come to the end of discussing how we implement the solution. So we can now move on to the implementation. But let me just make a quick point before that, which is about the running time of treble sort. Remember, I said that the running time can be as bad as n squared, but how do you show that it's never worse than n squared? Now that you know that treble sort is essentially performing two independent runs of bubble sort, you can use what you know about the analysis of bubble sort to argue an upper bound on the running time of treble sort. In particular, you can observe the behavior of the even and the odd subarrays independently and conclude that the outer while loop will never run for more than n iterations, and of course the inner for loop by design will run for exactly n minus 2 iterations every time. So the overall complexity is going to be order n squared. That's a claim that we had made earlier, so I just wanted to make sure that we have some sense of why it is true. So now let's take a look at the implementation. As usual, if you want to try this yourself first, this would be a good time to stop watching this video, get some coding done, and then come back and see if everything works out. So I'm just going to share the code snippets from the sample solution. As usual, you can find the sample solution from the official GitHub repository for these lectures, and there is a link in the description of the video as well as the course website. So in this part, we are just taking the input. There's nothing special about the input formatting. It's pretty standard stuff. There are t-test cases, and every test case is a number followed by the elements of the array given as space-separated integers. So you just read them all in. And the first thing we want to do is actually split the input array into these odd and even subarrays. So we just declare two integer arrays, and we run a loop that goes over the original array, and depending on whether the current index is odd or even, you pull out that element and push it to the correct subarray. Now, of course, the next thing we want to do is to actually sort these subarrays that we have generated. This is the part where we need to be careful about using an efficient sorting algorithm. So as you can see here, I'm just using the built-in sort function in C++, and as I said, your language of choice should have an appropriate sorting method that you can use. And once again, you could write your own sorting function as well. Just make sure that it's not bubble sort, right? Just make sure that you're using or implementing an efficient sorting algorithm here. This is crucial to ensuring that you don't get a timeout. Now, after this, you still need to put these arrays back. So that's what's happening in the second half of this code. So we declare a new array called sorted, which we are going to build out. Now, of course, this array that is named sorted need not actually be sorted. That's what we have to figure out. So maybe I should have used a variable name like treble sort output or something like that. But anyway, we will live with this. So what's going on with sorted? How are we building it? So essentially, it's the opposite of what we were doing previously. So here we were splitting the array, and here we are putting things back, trying to ensure that the sorted version of the odd subarray falls in place in the odd indices, and the sorted version of the even array gets into the even indices of this array that we are calling vsorted. So once again, you just run a loop, and you do different things based on the parity of the current index. So if you're at an even index, then you pull an element from the even subarray, and if you're at an odd index, then you pull an element from the odd subarray that you have sorted. So the way I'm doing this is that I'm always pulling what is at the head of the array, and I'm able to do that, and that's working because notice that I'm actually erasing that element from the array that I'm working with. So this is just one convenient way of doing it, but there are many other ways that you could do this. You could instead also have an additional index, for instance, that advances through these arrays instead of actually deleting them as you go along. So whatever way you decide to do it should be perfectly fine. So now that we have put everything back together, all we need to do is check if this array that we are calling sorted is actually sorted or not. And remember that if it's not sorted, we have to actually report the first inversion that we find, the first pair of adjacent elements that are out of order. So this actually is fairly, again, intuitive. You just go through the array step by step, and every time you are at the ith location in the array, just compare the ith element with the I plus 1th element, and if you have a problem, then which is to say that the ith element is larger than the I plus 1th element, then you can trigger a flag to say that, okay, this is not sorted. And in fact, the flag can also double up to remember the location, so that you can just output the value of the flag as the answer. So remember, I'm initializing flag to -1 just so that there's no confusion, because the first problem could even happen at the 0th index, right? For instance, in 132, the answer would have in fact been 0. So initialize your flag to -1, and when you come out of this loop, just check if flag is -1. If it is, that means that flag was never triggered, you never had a problem as you went along, and the array is in fact sorted. But if flag is a value that's different from -1, then the value of flag is actually the answer that you're looking for. It is the smallest index at which you encounter an inversion, an adjacent inversion. So you output the value of the flag in this case. And of course, the other details are pretty routine in terms of the formatting of the output and so forth. In CodeJam, it's pretty standard that they also want the case number and the literal word case spelled out and so forth. So just make sure that you get those details right. And then I think you should do well in terms of getting your code to pass. So please do try this out and let us know how it went over at the Discord community or on the mailing list. We will, as always, look forward to hearing from you. And in the next lecture, we will talk about a different problem, and I look forward to seeing you there.